Pleasure to join you even remotely. I can't, it's much nicer if I can see all of you in the room, but I can imagine all of you out there, and hopefully um, we'll have an interesting time here. I'd like to talk about a new era for solar and how it brings new research topics and new directions for the technology. I'll start by talking about how solar is coming of age. I think you're all aware of how much solar is growing, but some of you may not be aware of how much solar is growing and how it puts us in a new era for solar, and why this broadens the research agenda in multiple different ways. I'll talk a little bit about the PV technology development, where we've been, what are some current trends, and where some opportunities in the future. And I apologize, there were so many different things I thought of that I might include today, and I glossed over a lot of them, but hopefully you'll find something interesting here. So in terms of talking about how solar is coming of age, I think you all know that PV is growing rapidly. I'll talk, though, next about how it can be both 1% and 20% at the same time, and how we're entering a new era for solar. So to put in perspective how much PV has grown in the last years, if you look back to 2006 was the year when the tons of silicon used for PV surpassed the tons of silicon used for microelectronics. Now, I want to be clear, the microelectronics industry is still growing, so it's not like if you compare the bar in 2006 here with the bar in 2015, that you end up with seeing that that's how much bigger, because the microelectronics industries continue to grow. But you can see how really huge the industry is. And I'll come back to this later, that the market structure for silicon, when the demand for PV surpassed the silicon demand for PV, surpassed the silicon demand for microelectronics, it really changed some things in the market dynamics. If we step back more broadly, so solar electricity, here I've got on this graph world generating capacity, and then the different types of generating capacity. So the black bold line at the top is the total in the whole world. This is if you took all the PV, all the electricity generating plants, not just the PV, but all the fossil fuel, all the nuclear, all the hydro, and turned them all at full capacity at the same time. We would, back in 1980, it was about 2 terawatts, and now we're between, say, 5 and 6 terawatts that we would be able to generate. Then you can see the contributions by the different types. And very interesting here, solar is way down here at the bottom. However, it's the one that's growing the fastest. Solar now supplies about 1% of the world's electricity, which I'll show on this next slide. On the leftmost pie chart on this slide, I'm showing here this, and these numbers are all for 2015. I'm showing the electricity. These are in kilowatt hours, megawatt hours, terawatt hours, whatever units you want to use there. But the units for electricity are different than the units for capacity. And you see on this pie chart that solar has about 1% of the total. However, if you look at the capacity generation, generating capacity, solar is closer to 3%. So the reason that we have more solar capacity than we have electricity is that the solar systems are only generating electricity during the day, whereas some of these other systems may generate electricity round the clock. Actually, we don't have all of these systems generating electricity round the clock. Many of them are turned up or down, and in fact, some of them are designed as peaker plants to only operate an hour or two, or maybe 1 day per year during the time when the demand for electricity is the highest. But what you see by comparing this is that on average, the solar plants, we need about 2.5 times as many solar plants to generate the same amount of electricity as what the average rest of the electricity generating capacity is. Then if you look at the pie chart on the right side, this is using the same data as used for the middle pie chart, except now we've compared the difference between this chart in 2015 and in 2014. So I call that the expanded capacity. And what you see is that solar is growing faster than some of the others, much faster relative to what it's actually generating in electricity. And this is why I say the solar can be 1% of the electricity and 20% of the expanded capacity at the same time. And maybe an easy way to understand that is to think about, what if we started this year to sell 20% of the cars to be electric vehicles? And you know that in the first year, we could sell 20% of the cars to be electric vehicles, but we still wouldn't have that many cars on the road because there are a lot of other cars that have already been there for years and will be there for years. But if you continued to sell at that rate of 20% per year, every year for a few years, you would eventually get to the point where 20% of the fleet, this is assuming that they're retiring at the same rate, which is not necessarily a good assumption, but assuming that they're retiring at the same rate as the rest, you'll move toward that. And so similarly here, although solar is still very small in terms of being able to meet the world's energy needs, it's actually grown to the point where it's a substantial size. And in fact, if you look at this final pie chart over on the right, you see that renewable energy between solar, wind, and hydro is more than 50% of the expansions. And what that means is that if we want to do more than double, and this is from 2015, and these numbers actually grew in 2016. I'm sorry not to have them here. But if we more than doubled the renewable energy, the only way we could continue to do that would be to actively shut down some of the existing plants at a faster rate probably than what we originally planned. Indeed, if we take the data that we had on the previous graph a couple of slides ago, and now I've looked here, we're plotting both the capacity in the solid lines and then the expansions in the dashed lines. And these curves are essentially just taking the difference. If you take each data point on this top line and subtract 1 year from the next to see how much it grew, and do the same thing for solar. If you extend these, and think an interesting thing now is, sorry, this data doesn't go up all the way to 2017, but if you think back over the last, say, 10 years, from say 2005 up to about 2015, and now think of extending that relative growth rate. Now this is a log scale, so if we keep that same slope, then you would envision expanding it out to the point where solar begins to approach what we expect for the world total. This is actually a really fundamental thing that I think it's important that people understand. Solar has grown so much that we're now looking at bumping up against the ceiling. So can renewable energy continue to grow at the historical rates? The only way we'll be able to continue this slope of growth for the solar is if we also increase the slope for the world total. If we don't increase the slope for the world total, we're going to have to grow at a slower rate coming forward. So what this means is that we can adopt electric vehicles, we can look at generating hydrogen from solar, we can do lots of different things where people are currently using fossil fuels. And it's actually a beautiful thing about electricity that the amount of energy the world needs, if you generate electricity and run your car from the electricity, you don't need as much energy as if you get the gasoline and run an internal combustion engine, because the efficiency of the electric motors is higher than the efficiency of the internal combustion engine. So personally, my husband and I went and bought an electric car recently when I saw all these graphs and said, we all need to be working toward electrification in order to get a cleaner world. So this is where I view it's a new era, because the growth of solar has gotten to the point where continued growth of solar will require us to change the way we live in some ways. Another way that the growth shows up to change our research agenda, these graphs are from a simulation done by Paul Denholm here, and he was looking, the data he's using here represent California on a spring day, looking 0% of PV output up to 10%, and the 10% is not just on this one day, but over the course of time. But you can see the PV output on a sunny day in spring, when we don't have that much demand for electricity, may actually require us to begin to shut off some of the the plants that are normally running. And this really changes the way we run the grid and creates a set of research topics on how you run a grid with variable generation. We can usually predict from one day to the next when the renewable energy will come, but do we know how to actually make it run smoothly? The simulations shown in this slide were done at Berkeley National Lab by Ryan Weiser, Andrew Mills, and the group that they're working with. And what they show is the value of PV as a function of the PV penetration. And they've done a similar calculation for the value of wind as a function of the wind penetration. And what you see is that because the need for electricity is somewhat aligned with the demand for electricity, the demand for electricity is aligned with when the sun is shining. That is to say that we usually have the biggest demand for electricity on the hottest day of the year when the air conditioning is running full tilt. Because PV matches up with that well, it allows us to meet that peak demand very well and shows higher value than, for example, wind. The wind may not be blowing on the day of the year when it's hottest, and we need to run the air conditioning at full tilt. But as we now go to higher penetration, the value of the PV drops faster than the value of the wind does. And they explain this to me in that in California, and this simulation is done using data relevant to the state of California, that at any given time in the state of California, the wind is usually blowing someplace or other, whereas at midnight in the state of California, the sun is not shining anywhere. And so you see that the wind has a more constant value, whereas the PV falls off. And so another set of research questions is, what would we need to do to be able to retain the value of PV, even if we want to generate 30% of our electricity from PV? And for example, if you have very cheap batteries, and the prices of batteries have come down a lot in the last couple of years, if you have very cheap batteries, then PV actually can deliver the electricity when you need it. Even having just a couple of hours of storage to take you past sundown and into the peak in the evening can be very helpful here. So next I'd like to talk a little bit about where we've been. People over the years have often asked me, Sarah, what would be the winning solar cell technology? And I've often said to them, well, is there one winner, or are there many winners potentially? And if you look at batteries, we've used different kinds of batteries for different kinds of applications. And in fact, the kinds of batteries we are using currently have been evolving, especially with the introduction of the lithium batteries. But similarly, we may have benefit for different kinds of solar cells for different applications. There's also been a debate over the years of revolutionary versus evolutionary. For years, people have said that silicon can't make it, so we need a breakthrough to be able to meet the world's electricity needs. But we find that today, silicon is quite cheap and still dominates the market, even though we're getting up to a size that is close to what we need to run the world. Yet, there's still the question, will a different technology grow in the long term? With batteries, we've had some very well-established battery technologies, and now the lithium-ion battery coming along is displacing many of those others in some applications. Or in the case of PV, will silicon continue to evolve and remain the dominant technology? When we're trying to look at where we might go in the future, I always find it's useful to look at where we've been in the past. So this slide here shows how the technologies have evolved. You can see the blue and the black are representing the crystalline silicon technologies, the monocrystalline and the multicrystalline. And then the red is the amorphous silicon, the green, the cadmium telluride, and the purple is the SIGs. And so you can see quite quickly that silicon has been and is currently the dominant technology. Now, to better understand this graph a little bit of why cadmium telluride grew and then has lost market share, it's interesting to note that I showed you on the previous slide that the PV use of tons of silicon past the microelectronics industry and for the use of tons of silicon back in 2006. Well, that shortage lasted for a few years until the community invested in more silicon purification facilities. And it took a number of years for that to catch up. And during that time, people were wanting to install PV plants and weren't able to be able to supply those fast enough with silicon. And so First Solar went around and bought up all these projects where people couldn't get the silicon modules, and they were able to ramp their factories to do the thin film cadmium telluride deposition much faster. They grew into that void and in just a very short time grew to be the largest company in the world. So then the market dynamics shifted, and now we've been for a number of years in a surplus market where we're oversupplied with modules. And during that time, First Solar looked at it and said, we need to have a product that has an efficiency that can compete with the multicrystalline silicon. And so they spent some years in research developing a higher efficiency product. And now, if you read the news, you'll see that First Solar is talking about expanding their production, whereas for a number of years there, they were working more on improving the product. So market dynamics can interact, and it's not clear yet now that First Solar has a product that has the efficiency to compete with silicon and potentially is able to hit lower cost targets. Will they be able to recapture market share and eventually become king again, or will there be a new technology introduced? To understand the prices a little bit more, it's interesting to look back in the year 2007 to 2008. Module prices were about $4 a watt. This was during the time when there was a shortage, and the companies were actually making some good money during that time. Then as we moved into the shortage market, with time the price fell quite quickly. And in fact, today, the latest headlines are showing the price metric to be at about 35 cents a watt. With projections, they'll get down to 29 cents a watt. And there are rumors in India that people are able to sell at 20 cents a watt today. So the challenge for us in setting research agendas back in 2007, if you put in a proposal to be able to deliver a module technology at $2 a watt, that was really quite exciting. And if you could do $1 a watt, that was super exciting. And if you could do 50 cents a watt, you could get really excited. But if people are selling modules today for 35 cents a watt, and you put in that same proposal for a concept to get you down to 50 cents a watt, it's going to be more of a ho-hum thing of why are we interested in this when we already have technology that's gone beyond that. So the question is, what is the research opportunity today? Looking just a little bit more at the evolution of the pricing, here you can see the learning curve presentation of this, where we're looking at the price, the module price, as a function of the cumulatively sold shipments. And you can see that back in the 2007 sort of time frame, it was quite high, and now it's dropped low. And even in this slide, you can see it ended up, this data point ended up on top of this label, but you can see that during the shortage market, we were high. During the surplus market, then the prices dropped low. And this latest number, it's quite interesting. It's dropped even lower than what we would have expected. And the question is this just driven by the shortage market? Or I heard an interesting theory the other day that said that most of the module manufacturing is currently in China. And within China, there is little respect for intellectual property. And whereas in the United States, if you take a job with one company and then move to another company and share the first company's trade secrets with the second company, you may get sued. In China, that's kind of considered to be normal practice. And what you have then is a lot of sharing between the companies. If one company makes a discovery on something, that may get shared with the others. And it may not just be the people moving from one company to another. It's the fact that if one cell manufacturer figures out how to make a better cell, you may see that cell appear in many different modules. And similarly, if someone identifies a better encapsulant material, they may want to sell that to more than one company. And so you have that the innovations that are found in one company quickly spread to many companies. And we see that the prices for solar have dropped far faster than we expected, partly because the industry has grown faster and we've moved far out on these curves, but partly also perhaps because of the collaboration. So next I'd like to show you some of the current trends, and especially I'll show you some of the recent module designs that have been evolving. So here's an example of a new module trend, more bus bars. If we look over the years, the cell designs, originally when people made modules, they had one bus bar, and they found that if that wire broke, then the current would stop flowing completely. So then they used two, so that if one of them broke, there would still be another, and then they moved on to 3 or to 4 or to 5. Well, today, and the pictures I'm going to show in the next few slides here were taken at a recent exhibition in Shanghai. They have, if you've never been there and you have the opportunity to go, you should definitely go. It's a very large exhibition with many, many different things exhibited. This year it was in April. I think some years it may be in May, but it's in Shanghai and it's called SNEC, S-N-E-C. And here you can see the cells that have the 12 different bus bars. So some of the advantages of these, it improves the redundancy in case one of these break, but it also reduces the stress on each of the bus bars because each of them is smaller. So that may cause fewer cracks. The cracks may be less likely. There are also, I haven't shown them here, but there are also some new bus bar designs that are good at reflecting light in a direction so that it will be absorbed someplace else in the cell. So there's still a lot of research activity currently going on within the companies on how to improve the metallization in the bus bar design. Now here's another example. These are what we call shingled cells. You can see the appearance of these modules is slightly different. Instead of having square cells that are integrated, you see what looks like a strip. It looks like one big long cell, but it actually turns out that this is a series of narrow cells that are stacked so that they overlap with one kind of on top of the other. This was actually developed, to my knowledge, first by a company called Cogenra, and then SunPower purchased Cogenra and has been working on this technology. It has the advantage that it reduces the effective dead area. It also provides really a nice tidy appearance without so many gaps between all of the cells. But there could be some reliability issues. If you now look at, so historically one of the reliability issues with modules have been that if the solder bonds may break, and now instead of a solder bond here, there's a conductive connection between them. So when there's thermal expansion, it can flex a little bit and still be able to maintain the electrical connection between all the different cells. So this is a very different thermal fatigue problem now compared with when you have solder. So one of the first questions that we might ask is to be able to have confidence in the reliability of these new kinds of modules. Do we need to change how we test these modules? So this understanding this kind of connection of the cells is obviously a good research project right now. Another trend that we see is bifacial. These are typically glass-glass modules. On the left, I show you the back of a bifacial glass-glass module. And you can see here these 3 small junction boxes at the top. On the right is a building that has some of the bifacial modules installed in it in such a way that they allow some of the light to come through and into this internal kind of open area of a building. The light is reflected around then, and if it strikes the back of the module, will still generate some electricity. So the bifacial modules have the advantage that they can use light that strikes the back of the module. This will increase the energy yield, at least to some extent. And in some architectural situations, this partial transmission gives an attractive appearance. And so sometimes these are being used in creative architectural ways to make aesthetically appealing performance. I'd also like to note that historically we've had bigger junction boxes, and now we're replacing them with these smaller junction boxes. Again, this can contribute to a reduced cost because the total amount of material used in these 3 small junction boxes is less than the total material typically used in a single junction box. Another interesting trend, I should say for all of these, whether it's the glass bifacial, the shingled cells, the 12 bus bars, as I walked around the exhibition, we saw many of these across the exhibits in many different companies, some companies I never heard of before. And this trend with the half cells is one that appeared on many of the different places. This particular one is by Yingli Solar, but there were probably 10 companies that were displaying the half cell modules. So in this particular module, they use 144 half cells. They actually get up to 415 watts for this module, which is one of the highest powered modules I've seen on the market. The advantages here, first of all, you have lower currents, and I think you all know that the resistance losses scale with I squared R, so it's the square of the current. So if you have the current, you will cut the resistance losses by a factor of 4. Also, you may find that smaller cells are less likely to crack. If you load this up with snow and the module sags in the middle, the total strain put on the individual cells may be less because they're smaller. Now, it turns out that I saw 2 different configurations for these. You can either wire them to have the same voltage or twice the voltage of conventional, and you tended to see some of them where the cells were in the orientation you see here, which is more of a portrait orientation, but there were also some that were in more of the landscape type orientation. And either way, they could be made wired up quite easily. Another trend that is actually quite common to many of the companies is to what they call either an AC or a smart module. An AC module uses say a microinverter that when you connect the wires, instead of getting the DC electricity out, you get the AC electricity. The smart modules may also use the DC-DC optimizers to reduce losses from shading. So the advantages, in addition to the shading, the cells are less likely to be driven into reverse bias, which means they may be less likely to degrade and have problems. But perhaps very importantly here in the United States right now, there's a discussion going on with the firefighters where they are worried that if they need to fight a fire on a roof and one of these modules is here, they could potentially get shocked, and they'd like to be able to effectively turn off the module even when the sun is shining, so it's safer for them to work closer to the modules. And so these smart modules are able to be controlled and have the voltage controlled very quickly. So looking then at some of the new research opportunities, I've already touched on many of these. We have some of the same themes that we've had for years of lower cost, improved efficiency and reliability. But then we can also look at things like higher efficiency with optical management, looking at aesthetics, looking at lower operating temperature, many reliability issues. I think it's really important that as the price or the cost of the modules goes down, as we've seen in the last 10 years, it's dropped by more than a factor of 10. As you squeeze the cost out of these, do they still work, or will they have new reliability problems? And one of the things that people suggested to me years ago was that as you're trying to squeeze the cost out, you try to use less materials. So you use thinner frames, thinner pieces of glass, thinner cells, and you'll find that many of the new problems that come along may be mechanical in nature, which may be very different than what historically we've seen for failure mechanisms in the field. And finally, I'd like to touch on new form factors, reduced weight, and things that allow us to get into new applications. Here is an analysis that's been done by the Department of Energy showing how they had benchmarked in 2015 the idea that the electricity for a solar power plant may be on the order of 10 cents a kilowatt hour. Well, nowadays you see headlines for much less than that, but it's an interesting thing to evaluate where the opportunities are to reduce the cost. Um, Early on, it may be that you can find one thing to say, if I could fix this, I could reduce, I could halve the cost of the electricity. At this point in time, the PV systems have been so well optimized that it's very difficult to find a single thing that will make a huge difference. But here you can see that if you can reduce the module prices, that will contribute to the overall delivered cost of electricity. If you can improve the efficiency of the module, it will save on the balance of system costs. If you can improve the reliability so that and the lifetime so that the products don't degrade as fast and so that they last longer, or if it costs less to maintain the system, and if you can reduce the installation costs and other the financing costs and various things, there are opportunities in many, many different ways to reduce the costs. So you could see that we could end up talking for hours about all the different research topics. Here's an interesting one about what's happening as the cells become closer to reaching the theoretical maximum. Now, every solar cell emits light. It may not be apparent to people, and in fact, for years people had the conception that because silicon is an indirect material, that it would not be able to emit light. But in fact, silicon does act as a light emitter, and we use that feature of it to be able to um, diagnose cracked cells and various things quite routinely. And here in this case, I created this graphic to show what goes on in a gallium arsenide cell, in which case you have a gallium arsenide substrate with an active gallium arsenide diode grown at the top. And within that layer, you will have some light emission. And if the light is emitted in a direction that enables it to go out the front of the device, within what we would call the escape cone associated with the difference between the index of refraction of the gallium arsenide and the air, it will go out and contribute to the external emission. And that's actually a good thing. It's counterintuitive. Often you might think that that's a bad thing, but it's actually a good thing. I'll come back to that in a little bit. If it comes in a different direction, it may be totally internally reflected within the front of the cell, and then it may go elsewhere, and whether it goes down into the substrate and is absorbed or is maybe absorbed in a layer here, if it bounces around and maybe hits a grid line or something, any place it may be absorbed, it may be lost. Additionally, if the light is emitted down toward the bottom of the cell, this will be a loss of that light. Now, if it's reabsorbed, if it's confined within this active layer and reabsorbed, then it contributes again to the potential for electricity generation. And so this is why we call it photon recycling, because these photons can potentially be recycled many different times. Well, for years when I looked at this, I thought, well, it's just a factor of 2, whether it goes out the front or out the back, it doesn't really make a big difference. But then what I hadn't thought about is that only about 2% of the light goes out the front here, because most of it is internally reflected. If you can remove the substrate so that you now also get the total internal reflection at the bottom layer, you do a much better job of confining these photons into this layer, and you actually have the theoretical potential of going up about 80 millivolts. In practice, it isn't actually that much. And it is counterintuitive, but if you're looking at the detailed balance approach to looking at the thermodynamics of what's the highest efficiency you can achieve, the Shockley-Queisser limit is dependent upon the external emission. And it turns out that it's the external emission that the detailed balance, looking at this as a black body using Planck's law of radiation, you can calculate what will be the external emission. The internal emission, where you may emit and then bounce around and be reabsorbed, is actually a somewhat complicated thing to model, but the external emission is actually quite straightforward to model, and that's actually what it turns out to be the ultimate thing that limits the performance of the cell. And you'll see if you look at the efficiencies that were achieved for gallium arsenide when Alta devices began to implement the gallium arsenide cells in a thin film configuration, that they very quickly set some new efficiency records. Well, what happens if you try to do this in a multi-junction cell design? Now you have the problem that you need to have a selective reflector behind each of the different junctions. Now, many of you may look at this and say, well, this is fine for gallium arsenide, but it turns out, perovskites, the special thing about perovskites, they're actually very good emitters too, because they seem to be so insensitive to some of the non-radiative recombination that you actually see some bright emission from them. And even silicon cells nowadays, even though you don't think of them as being effective at emitting because of their indirect nature, the highest efficiency silicon cells today are seeing a substantial fraction of their loss associated with actually the radiative recombination, not just the non-radiative. So this is a topic that, although the work was done originally in the 3,5 cells, you may find it useful to bring it to other types of devices. Just to give you some idea, a little more detail of how this can work and how it plays out, I was talking about, here's a schematic for a gallium arsenide cell. And if you have a gallium arsenide contact layer that's outside of the active part of the device, but this contact layer may be absorbing of the light, if you now have emission within this gallium arsenide active device, then when the light bounces around, it may get absorbed by this contact layer. This study was published by Miles Steiner and his team in 2013. And what you see here is as a function of the thickness of this layer, you get more and more absorbance, and as you move out, you expect that the voltage may be decreased. And in general, that is the sort of thing that we see, and the theory behind this allows you then to separate what fraction of this is the optical loss versus the electrical loss. And you can see that for a design out here, these cells are actually dominated by the optical losses. And so understanding the optics in these devices is what you have to do to be able then to improve them to reach the theoretical limits. I'd like to look next then a little bit about how aesthetics can matter. I think you're all aware for a rooftop, you'd like to have something that is the more uniform black is good. You can extend the aesthetics theme to many different colors. These are not so common. But one that is now developing, and again, these next slides have photos taken this past April in Shanghai. You can see how Suntech has made a roof here that is pretty much all solar panels. So instead of having the solar panels up on racks that are maybe at a funny tilt angle or something above the roof, these actually become the roof. And here I have an enlarged version of this. You can see how they put the modules in and kind of connect them together with these interconnecting layers. And this can actually have a quite attractive appearance. And if it can actually replace the roof rather than being mounted on the roof, it may help to reduce the total cost of the system. And specifically, things that are attractive here is you're looking at how to research and design this sort of thing. An attractive appearance, a high efficiency, being lightweight, being able to operate at a low temperature, and being reliable are some of the obvious attributes we'd look for. Now, that one I just showed you, it's not clear if those modules are going to operate at a high temperature. This is another version. This one is by Yingli, where they've kind of tiered or somewhat shingled each module, and you can see in this close-up where there are vents that go along the edge of each of these that allow the air to flow up underneath of the modules to help keep them cooler. But you can see that in general, these have a fairly nice uniform black appearance. In this particular case, I was taking a photograph indoors where there were some lights that are reflected, so it has kind of a funny appearance here. But when you look at this, especially when you look up close and you can see the individual cells and where the edges of the cells are, these have a very attractive appearance, and again provide you a way to actually replace the roof instead of being mounted on the roof. You're all familiar with what Tesla is doing. I'm not going to spend time on this, but it is another example of how we can make the roofs look quite attractive if we put the effort into it. Now, this one's a little bit more controversial. We have debates at NREL where whether we should actually be talking about PV on roads or not. This was a sidewalk a design that was exhibited again in Shanghai. You can see the child is somewhat intrigued by the appearance of these solar cells here. Some of the advantages of this are the potentially attractive appearance, depending upon how you do it, and it can enable lighting underneath of the sidewalk. And the surface can actually be, the glass can be quite robust and last for quite some number of years. It's quite controversial whether you could actually make roads that cars would drive on that would be able to do well. And obviously these surfaces can easily get dirty. But it's an interesting thing that if you look at the roads and parking lots within the United States, that if you took that total area and put PV across all of it, you would have something like 3 terawatts, which is more than the total capacity of electricity generating capacity in the US today. It's an interesting thing there that although building it into the road itself may be difficult, finding ways that the solar panels can be alongside of the road, if we end up transforming our fleet into electric vehicles, if we could use solar power generated all along the roads, it would allow us to deliver the electrons in the place where we need them. And so it could be quite intriguing whether we're able to do that. Some other new products here is a product by Hanergy that is colored windows. I'm not sure how many people want blue and orange kinds of windows, but they're quite interesting. Another one is to reduce the weight. Why would we want to reduce the weight? Well, there are many buildings out there that don't have the strength to hold the PV panels, and strengthening the roof adds substantial cost. So if we had lighter weight panels, it could potentially enable their deployment in some places where we can't now. Now, there are lots of different strategies for this. So silicon panels use glass for rigidity to protect them so that the cells don't crack. Now, on the other hand, the cadmium telluride and SIGs often, although they don't have wafers that will crack, we find that typically if you grow them on glass at the higher temperatures, you may get higher efficiencies. But if you can figure out how to grow these, or maybe it's perovskites, or in the case on the right here, you can see the gallium arsenide that's been, say, grown on a wafer and then transferred over. If we can figure out how to deploy these, the amount of material needed is quite small, and with the lightweight and flexible nature, it opens up lots of new applications. So again, these are possible research topics of how we could achieve some of these. In this particular case, we see an Alta Devices gallium arsenide set of cells that have been put on a drone. And this is actually a very interesting market. The people who are flying the drones are very interested to be able to have the flexible cells that can conform to the shape of the module, to have the high efficiency. So these gallium arsenide cells can probably make modules that are above 25%, and the cells themselves can be above 28% efficiency. They can be quite lightweight because the thickness only needs to be something on the order of, say, 2 micrometers. And if made carefully, they can be quite attractive and quite reliable. Here, in fact, is an example. You can see the drone here with the cells on them, but also then a car. And again, we have reflections from the ceiling of the exhibition hall. But this car has been covered across the top and the roof in the hood in front and even along the edges here with the solar panels. And I think that they can get something on the order of a kilowatt of the solar panels onto the car. Still probably not enough by itself to be able to drive the car, but it certainly will extend the range and give some flexibility that if the batteries are running low, it gives an added source of the electricity, and also enables being able to keep, say, the car cool during a hot day. The PV industry has now grown to be huge, something approaching 100 billion per year, and it's a natural part of the we often call it the S curve of technology development. You start with R&D, move into product optimization, and then you can move into reliability optimization. And so there's an opportunity to spend more time on reliability studies. It's a difficult thing that if you're wanting to accelerate a process, the question is how much can you accelerate it? And here we show the example of if you want to accelerate the aging of an egg, to be able to accelerate 25 years into 3 months, which is kind of what we'd like to do for solar panels. It's like trying to hatch a chick in 6 hours. And I think that if you know how to do that, you should go into the poultry business. In the meantime, we're still trying to figure out how to do that with the solar panels. And here I show that people commonly are wanting to launch a new product about every 6 months. The standard qualification test is on the order of about it can be completed in less than 3 months. And if you're wanting to bring in new material into the factory and you're worried that you might have some contaminant in it, you'd like to be able to test it in a short time. And here's what you would need to do. If you can only accelerate a process by a factor of 10, which is what we observe for some of the processes, it will take you something on the order of 2.5 years. To get down to the desired time, we need to be able to accelerate by a factor of 100, and that's like trying to hatch the chick from the egg in the 6 hours. I do want to leave a few minutes at the end for questions, so I'm going to try to wrap this up quickly, but to say there are lots of different failure mechanisms. Historically, modules have tended to discolor. The statistics show that almost all of them show, the older ones show some discoloration, but people have found how to test these materials so that they tend not to discolor as much. We also see failed electrical connections, and something as the modules become thinner, they become susceptible to being cracked. And we're seeing in the field today commonly cracked cells. Not all of them are quite as bad as this one. But in the end, though, the holy grail of reliability is to be able to do a service life prediction. So if you're looking at potentially all these different types of failures and lots more, a question is, what would you need to do to be able to understand what's going on well enough to predict the life of a module? And I say to people, it's really easy to do a prediction 25 years plus or minus 25 years. The hard thing is to do a prediction of, say, 25 years plus or minus 1 year, or even plus or minus 5 years. So in this graph, I'd like to show you some examples of, let's say you define a test that you can do on a product, and according to your analysis, it shows that if it passes this test, it should have an expected 25-year life. And let's say that you've assumed that based on having measured a reaction process that has an activation energy of 1.1 eV, and you did your analysis in Munich. Well, what if now you have a different bill of materials? Maybe there's an impurity in a material, and it changes the activation energy. It may be now passing that same test. If you rerun your numbers, now realizing that the degradation mechanism may be different for this module than the one that you did all your studies on, you find that that module may only last, say, 3 years. And that means you now have a prediction of 25 years plus or minus, say, 22 years. Not very useful. Similarly, let's say that we had put it in Munich, and now we think we might use it in Phoenix. I say to people want to walk up and say, here's a 30-year module. And I say, if somebody says that to you, I wouldn't believe a word of it. If they walk up and say, this module will last 30 years if deployed on the roof of this building with this tilt angle, then at least you think they maybe did the experiment. But if they just say this module is going to last X number of years, and they haven't said where it is, you have no clue. The difference between the rate of aging in Munich versus in Phoenix shows that a module that might last 25 years in Munich might only last 2 years in Phoenix. So here you have the prediction of 25 years plus or minus 23 years. Similarly, if the process window, let's say that you allow the thickness of the solder to vary. Some solders may be thinner than others and then may wear out faster. again, you may have a different lifetime associated with passing that same test. So to have meaning in a prediction of a lifetime, you really need to fix exactly what the product is, where it's going to be used, and how it's made. What's the process window by which you accept it to leave the factory? So people are often trying to look at the service life prediction, but it's actually very difficult to get the uncertainty down as low as we'd like. So just in conclusion here, I've talked about how solar is growing fast, how we're in a new era in which solar growth must either slow or we need to increase the electrification, decreasing our energy use of the fossil fuels directly or other fuels, and move toward more electrification. I've shown you examples of some new module designs, the bifacial, often with glass structure, using maybe half cells or shingled cells, or the smart modules, and some with new form factors that may be flexible, that could be rolled out or integrated onto a drone or a car, for example. Here I show a picture here for trucks that need to have loads that are refrigerated. If the truck wants to stop someplace and if they have a no idle zone there and they have to turn off the truck, then they have to power the refrigeration system from a battery. And having solar panels on the roof means maybe they can get a decent length nap instead of a very short nap while the battery runs down, running the refrigeration unit. And finally, what I've talked about with the service life prediction will require us to control the use environment, the bill of materials, and the process window. And I want to thank there are many different groups I've worked with over the years. This is obviously not just something, a summary of work I've done, but summary of what's happening in the industry. And I want to thank you for your attention. And I think I can take any questions that you have at this point. Or should I go back to the chat window to see if there's any questions?
You know what? If there are questions, I can let you know.
Okay.
It's up to you though if you'd prefer to see the chat window yourself.
No, that's fine. You want to read them off to me if there are?
Sure, absolutely. So, does anyone have any questions for Dr. Kurtz? It looks like we've got one coming in via chat. Just
okay.
okay. Here's one question. They were curious. India has recently said they were hoping to transition to all electric vehicles sold by 2030. Do you have any thoughts on whether that's viable or expect?
So electric vehicles are growing very fast. So one thing to be aware of is that there are a lot of electric vehicles in India that are probably smaller than some of the vehicles. They have some little scooters that move in and out amongst the traffic, which is actually a real asset in India. And we see actually electric vehicle sales going up very quickly. Whether they can make it by 2030 to be 100% is obviously a tough one to call. But I guess the question we'd have to ask is, what would be the limiting thing? Would it be limited by our ability to get enough lithium? Is it limited by our ability to build factories that can make the electric cars? I personally am quite optimistic. In India, if you've seen the level of pollution and the way the roads work, I think that electric cars will be quite popular, and I would love to see them adopted by 2030.